Okay, welcome back for more of Odinmade Hero, the series where we follow Casey Muratori and try and learn how to make a game from scratch. Learn how to make a game from scratch from him, but not totally from scratch because we're going to learn how to do it in Odin instead of C and C++. I'm starting to really enjoy looking forward to this time of day where I can just not have to deal with anything other than writing the code. Although yesterday was pretty math heavy, and it was actually 2 days that I was able to cover yesterday where Casey went over a bunch of the math at a high level, and then we started digging more into vectors specifically and how to use them to just start kind of coupling these X and Y coordinates and then eventually the Z coordinates for our tile map stuff and also for our drawing code. And it's been good. I finally got my first taste of Odin's array programming, where we can just very easily, if I can find, what am I looking for? Offset, here we go. I can just very easily start working with vectors using Odin's array programming, and it's a pretty good feeling. It's something I had been looking forward to since I had found out that this was even a feature. And so we're just going to go ahead and jump right in and use more of it today. I'm kind of time boxed by whenever my oldest son wakes up from his nap. That'll be the marker for the end of the stream for me. So I'm going to get through as much of this as I can. I think we're just going to be working with dropping in more of these vectors, using vectors more all around the code base, but specifically with respect to motion. And so with that out of the way, I'll go ahead and let Casey, kick it off.
Start recording. And now we can begin. Now that I'm sure there's no little snafu there. Okay, hello everyone, and welcome to Handmade Hero, the show where we code a complete game live on the interwebs using absolutely nothing, no engine, no library. We program everything ourselves from scratch, as basically both for education purposes and for just for fun, honestly, because I like coding things from scratch. And so today we have something fairly important that we have to tackle, actually. So I don't want to waste too much time before we get right into it. So I will simply say, if you are following along with the code and you have pre-ordered the game on handmadehero.org, you should have gotten a link in your email. In that link, there's a zip file, and in the zip file there are zips for every single day. You want to unzip day 42 source code because it's day 43 right now, and we always start with the previous day's source code. So if you unzip that into a directory somewhere, then you can start coding exactly where I am coding right now, and so you should be able to follow along precisely. So let's go ahead and get started. Like I said on the when I posted on Twitter today, what we're supposed to do today is we are actually supposed to get ourselves a little bit closer towards having some good player movement code by taking a look at the equations of motion, which are basically the physics that underlie how real things in the world move, understanding them, and then figuring out exactly what part of them we want to use or what we want to do in order to create something that feels good to play, which is not always the same as making something physically realistic. Usually what you want to do in a lot of scenarios is you want to kind of know what the physically correct thing would be, because the right thing to do gameplay-wise is often close to that thing or has a lot of the properties of that thing, because people's brains are obviously attuned to work the way physics works, and to think about things the way physics works is what they have experience with. But it is also often the case that you don't really want a perfect physical simulation most of the time, because we want to kind of go more towards what's fun to control, not what it would be accurate, right? We're not trying to make a simulation here. Some games are trying to be simulation-y, and those games should care a lot about how accurate their physics are. But in our particular case, we're more concerned just with how the player, how sort of that hero character feels to move around. And so in that case, what we really want to do is just kind of know what the equations of motion are in the real world, and then go ahead and take the opportunity to sort of like bend them a little and make up essentially some equations of motion that are whatever we think feels the best just from playing with it.
I mentioned this weeks ago, like probably that first week of streaming after I had started the new channel. And basically what he just said was what I had said at the time. And I was just, quoting him when I was saying that having a good understanding of physics is an important piece of making gameplay that feels like it's something that you can navigate as a human being, which is it resembles the world, the real world physics that you come across in day-to-day life. Like if you drop something that's light, if something has, if something's like a softball, like something that's, more dense versus something that's light, like a balloon or something, like you can kind of intuit those things better when they behave more realistically. But like you just said, you can't make it too realistically, because then you get like into simulator territory, which if you're trying to make flight simulator is all well and good, but that's not, if that's not what you're trying to do, then you want to be able to understand, right, how to differentiate those things and make things more realistic where it makes sense to, in the case of, you're making flight simulator, or you want things to be less realistic but feel better. And that feel part is very hard to pin down, right? That's the nebulous thing that it takes probably time to refine a good understanding of how to implement. So let's learn how to do it.
And I don't even know exactly what those are going to be ahead of time, right? We're gonna see by sort of just trial and error what we end up thinking is the most interesting way to have our character be controlled. Now, if you remember yesterday, what we did is we started replacing things with a vector structure that we had. We actually turned it into, just at the end of the stream, we turned it into a union. It's basically just this right here, and all it is it's a...
Oh yeah, so this came up in the Q&A yesterday, actually, the way that he is structuring the union. Before he was doing like an operator overloading of that bracket syntax here, where he's indexing into the same memory that is held within this struct, right? That X and Y, X is slotted in as the first element of the array that he's defining here, and then Y is slotted in as the second because it's a union. He also pulled this union here out of another struct. And so I think he called it an anonymous struct, right? And this was how he actually did it originally. I was talking about the game controller input, which is over here. And this is kind of doing that same thing, which is actually different from what he did originally, where he had it set up to overload that operator syntax. And the reason why he did it, he was trying to do it this other way, is because he was talking about, and again, this came up in the Q&A, like other people were having issues using different compilers where that approach of using like an anonymous struct, right, or an anonymous union too, because in the case of when he had the union inside of the struct, before he pulled it out and to just be a union, the union was anonymous too, right? And then down inside of that union is where this memory was laid out. So anyway, it was interesting to see that you could actually do that multiple ways. I didn't even pick up on that originally at first, but the more you know, right?
XY pair, right, like that. And we then went ahead and made all of our code kind of start working with that XY pair, just kind of sucking that up a little bit, and so made a lot of things that were verbose a little bit more straightforward. And we didn't actually spend the time, because we kind of got to a little late in the stream, to actually condense everything that we could have condensed. Certainly, we still left a fair number of things in scalar, or even though we were doing them in vector, maybe still left the math as two separate things, one for x and y and that sort of stuff. So we haven't done too much work to condense our code, but we did a little. And I don't really want to go crazy with that right now, because we can always do that later, and there's really no particular need to change working code at any particular time. So rather what I'd like to do now is just kind of concentrate on this this player P thing here. Maybe we'll think about looking at the camera P as well, but this player P is basically something that we have, which is just saying here is where the player actually is in the world. And what I'd like to do is start thinking about that in terms of how we want to modify it and how we can make it feel a little bit better. So if we actually run the game and just look at what the game has right now, you can see that the character motion, we talked about this already, just does not feel particularly good. It's kind of, as you move around, you just kind of feel like it's, it's just the most basic thing. It just kind of, it stops instantly. It doesn't have any kind of acceleration or anything to it, or any feel there. It doesn't have any momentum, so when I let go, it just kind of stops immediately. And there's really there's nothing good really about the feel of this particular, about this. And so what I want to do is start to fix that by, let's just, just kind of adding in some basic stuff, give it a little bit of that momentum, give it a little bit of that, like it accelerate and decelerate, just to give it a little bit of that feel. And we don't want too much in that. We don't want a crazy amount of acceleration and deceleration, because we still want the player controls to be nice and tight. This is an action game. We don't want the player to feel like it's super soupy and kind of really hard to like stop where they want to stop, but I just want to give it a little bit of something. And so what I want to go over first is just to sort of say what sort of the background is here in terms of what actually happens in the real world in terms of things that are in motion. And so what happens in the real world, right? If I've got something, this is going to be my like magical sphere here. Maybe it's a magical sphere with a little reflection on it. It's like a bowling ball or something like that. So I've got my little sphere or something, and I want to start talking about how this thing moves around. Well, obviously there's some basic things that happen with any physical object in the world. One of them is that it is constantly subject to a downward force, and we all know what that is, right? That's gravity. And gravity is a very interesting kind of a force, actually, which we can talk about a little bit more later. We won't really have to think about it too much for moving the character, because he's not really falling. He's always in contact with the ground, and we assume that like the gravitational forces are getting handled by his little sort of stumpy legs things that he has under there that kind of keep him on the ground or whatever. But point being, everything in the world is constantly under gravity. We know this. So there's always kind of a downward force that's at play there. And it's actually more of a downward acceleration technically, but again, I said, well, we're kind of think about that a little bit more later. We don't have to worry about it too much now. And then anytime that any object is going to move, it's basically the way in which it moves can be broken down into sort of two distinct, I want to say categories, or two things you have to think about when you think about how an object moves. And when I say this, we're talking about basically, I'm going to just preface this by saying, oops, that this is rigid body dynamics that we're talking about here, which is specifically talking about sort of the way in which matter in the world moves when you reduce it down to the basic concept of just let's assume that all of the atoms and quantum physics and all of that stuff that makes up my little bowling ball sphere thing, let's take those out of the picture and just say, if we just assume they're all rigidly connected right now, and we're not talking about what happens when the ball breaks or what's happening at a molecular level and all these sort of things, we're just talking about...
Well, shoot. So lots of whiteboarding the past few days. There's a similar thing yesterday where he goes over a lot of the math I think I'm just going to sit through this and do my best to digest it, because a lot of physics-specific math is not the kind of math that I am easily, or not easily, but, well, yeah, easily acquainted with. Like, it was harder for me to intuit physics-related math. Not that it's, like the basics of it are super complicated or anything, but linear algebra, for whatever reason, was just something that I understood, on its own much more quickly than because I remember I took a physics class as part of my university courses, and it was just a really bad class, and I don't even think it's worth it to get into the details of why, but it was just very poorly implemented, and so I actually dropped that class like 3 weeks or 4 weeks in, and focused more on programming classes. Actually, that was one of the things that incentivized me to go more towards programming, but I should really digest this and take the time to make sure I understand it properly. I just wish that I'd seen that this was going to be another heavy whiteboarding day, because then I would have pre-watched it up to the point where he starts the code, and then maybe we could have knocked out 2 days. But it is what it is. I'm just going to sit here and let Casey's 1.5 times speed voice enlighten me.
How the gross, large sort of body that these things form move around. There's really two ways that we have to think about that. One is called linear, and the other is called angular, right? And they are sort of exactly what you would think. You essentially have to think about how the thing moves around. So like the path that this thing is taking through space, right? How is this thing moving? That's linear, the sort of the linear dynamics of it. And sort of the angular dynamics of it are how it's rotating, right? Because this thing could spin around, right? It could do all sorts of things that induce sort of like a rotational motion, even if the thing is sort of standing in one place, or sort of sitting in one place. Now the physics behind these two things are not actually different at the lower levels, because again, everything is just a bunch of atoms, everything's just a bunch of quarks, however far down you want to go. And those things all have physics that determine how they work, and they aren't separated into whether the motion of the atom was about the ball rotating or whether it was about the ball moving. So down at the molecular level, it's not going to be about what the bowling ball was doing out where we observe it, right? But in terms of our simulation of it, where we are making this reduction and saying we're not thinking about atoms, we're not thinking about any of that stuff, we're just thinking about it as one sort of gross object, because we are treating it all as one group like that, we have to think about both how it moves in space and how it spins, because those two things are necessary to figure out where all the atoms actually were when we go to actually say, okay, where is the ball now, right? So what we're going to do today is we're going to focus on this part here. We're not going to talk about this part, which is why I picked a bowling ball, because hey, a sphere, you don't really care which way it's rotated to some degree in terms of how we're going to draw it. So if we're just moving around, I picked something that'd be nice and easy to think about in that case. So we're just going to talk about the sort of the linear portion of things. We're just going to talk about the movement. And so the movement, basically we have forces in the world. That's like when I go to push on this ball with something, right? When a hand comes in and I just kind of smack the ball, or if something else hits the ball, like another ball comes in here and smacks the ball. Basically we have forces that are applied to this object. And those forces are all actually acting for the purposes, again, of the rigid body dynamics sort of way of viewing the world. You can think about reducing this object and all of its complexity down to basically just its center of mass. So basically the center of mass, which is if you think about the entire sort of all of the matter that's in this thing, if you think about just thinking of where that's centered, where all of it, if you look at the point that basically, if you averaged how dense it is everywhere in it, and figured out the center point of all of that density, you would get the center of mass, which is basically a point which, if our sphere was uniform density, would be like right at the center, right? And again, a lot of this stuff is stuff that you'll only care about if you start to actually do real physics stuff. I'm just mentioning it so you can kind of know what we're talking about, right? So we don't have to think really about densities and masses too much, but it's just something, mass may come up a little bit, but point being.
If I'm thinking about like one of the notions I have of making kind of like a game prototype, because I'm very far away from doing anything that's like seriously ambitious to the point of like, let's make a whole game, like a 10 to 20 hour game that keeps you engaged and actually offers like gameplay that's interesting enough to keep you hooked into the game for that whole length of time. Before I get to that point, I'm thinking about all of these things. And so what he's talking about is relevant to one of those sort of prototype ideas where I'm thinking about what are all the things that I'm going to need to keep in mind moving forward, in particular, to try and go and implement that prototype. And maybe we get to a point with the series where he's doing that sort of thing anyways, but like he's talking about here, like density will be relevant. For instance, if I want to have a game where there's some kind of melee combat and I've got a sword and I want that sword to move quickly through the air, because you can hack and slash quickly with a sword, versus like having a sledgehammer that's two-handed or whatever, and it takes a long time. It does more damage or whatever, but it takes a long time to swing down on top of the baddie's head. So for that reason, it's weird, because I just want to hurry up and get to the code, but at the same time, if you don't understand the problem space well enough to actually stick through and get to that understanding, then it doesn't matter how much code you write, you're not going to know what to write. So I have to temper my expectations. You gotta earn that knowledge.
If you're doing full 3D stuff, you would start to care about a lot of this stuff. Anyway, so what we want to think about is we want to think about all of the forces that are applied to our object. Okay, so all of these things that might be pushing on our object at any given time. The gravitational part of it, the things that are pushing on it directly, impacts that are happening, those sorts of things. All of these things we have to consider in terms of figuring out where the center of mass of our object goes. And at the end of the day, on any given instant, what we want to do is look at all of these forces and determine, due to all of the forces that are impacting this thing right now, where is it going to be pushed? What is the net sum total of all of the forces on this thing? How is it going to be pushed, right? And now there's a very fundamental equation that you probably have seen before if you took high school physics. Again, it looks like this. It's F equals ma, and what that basically says is...
I actually don't think I ever had like a proper physics. Maybe it would have been... What grade was chemistry? Chemistry was like 9th grade. I can't remember if I even had a science class in 10th grade. But certainly like this very, basic force equals mass times acceleration equation. That is something that I can certainly think back and remember is hidden in the recesses of my brain. There was something else that he mentioned that just made me think of something. I'll see if it comes back.
Force equals mass times acceleration. And the reason that I point this out is because forces, which are the things that push on this ball, right? Wind could be a force, for example. Something directly pushing on the ball. Gravity could be a force on it, et cetera, et cetera. All of them are forces.
Oh, the gravity constant, being 9.8. That's the only thing that sticks out in my head. And that is all relative to... There was a great... well, I'm assuming it's a great blog because the guy that posted it sure seems to know his stuff. He's one of the main... people I've seen like online, putting stuff out online that works with Odin. And the spelling is different from what I'm used to seeing, but his name is Jacob. And he posted a blog about enforcing like a time step that is constant in his game loop. And I need to bookmark it and come back to it because it's relevant to this entire day's lesson about equations of motion, because that ties into all of that, right? Like if you want, it's not enough if all of the math involved in calculating the motion in your game code is perfect. It doesn't matter if your time step with your frame rate is not enforced. And I think we're in a pretty good state. That was what Casey set us up for success with the initial platform layer to an extent, but I'm sure there are things that he comes back to later on to polish. So just trying to keep all of that bigger context in my mind as we look at this stuff.
And the degree to which they affect the ball. Remember, the acceleration is what determines what's actually going to happen to the ball. The acceleration that those forces produce is mitigated by the mass. The mass of the object that's being moved basically determines how much each individual force will actually affect the object, right? So if we look at what all the forces are, and then we want to see how much the sum of those forces will affect our object, we have to think about what its mass is, and we have to solve this equation basically for A, right? So it's pretty easy, right? Because it's just F over, right? If I want to solve for A, all I do is divide by M, and I get F over M equals the acceleration, and that would be the equation for the acceleration. So basically, the heavier our object is, the less it would move for any force, right? Because as the M gets bigger, the acceleration goes down for any given force, and that's exactly what you see in the real world. The heavier something appears to be to us, the harder it is to push it. That's just the intuitive way to think about this, right? There's a lot more involved there, but that's basically an intuitive way of thinking about it, right? And so, if I want to start talking about how physics actually works in terms of how it affects something like a rigid body, like a bowling ball or whatever it is, or our little guy there, essentially what I want to do is I want to talk about summing all the forces on him. I want to talk about computing what the acceleration actually is for all of those forces combined, right? And so I do that by figuring out what the mass of the guy is, and I do my divide, and I get out an acceleration. And then, again, I have to figure out how to relate this acceleration back to a position, right? Because what I want to know at any given time when I need to render this bowling ball, or whatever it is that we're simulating, I have to know where in the world it is. That's like the primary thing I need to know in order to be able to display it on the screen. It's also the primary thing I need to know to be able to do collision detection or anything else. I need to know what that is. And so that's where we get to sort of the hierarchy that you've probably seen before, hopefully, but maybe not. But position, velocity, acceleration, right? And this is what I talk about when I say the fundamental equation of motion, the very simplest stuff that moves things around. It's a hierarchy.
Let me see if I can say this right. Anybody who understands these three things, and he's about to, I think, explain that, and understands the math, the way they're related in the math well enough, will immediately be able to say this, just from like, they just internalize that knowledge so much, but it's been a while since I've looked at this, and then I'm quite sure that the first time I watched this months ago when I was working through the project in Zig, I just kind of zoomed through it so I could get to writing some code. But what is it? Going down, these are all integrals of each other. Velocity is an integral of position, and acceleration is an integral of velocity. I think I have that right. And then velocity is a derivative of acceleration, and position is derived from velocity, right? Let's see if I'm right. Let's see if I remembered that much at least.
That looks like this. And all of these things are essentially dependent on time. Okay, physics is all about what happens to things over time, and so what we're talking about when we talk about doing sort of rigid biodynamics or physics or anything sort of thing, we're talking about looking at this hierarchy of information about one of these objects that we're moving around or doing whatever to.
All right, rate of change is the thing that comes to mind. So velocity is the amount to which position changes over time, and then acceleration, right, is your rate at which your velocity is changing over time. So if you're accelerating, you're picking up velocity, which is making your position move more quickly. That example is of what a derivative is and what an integral is, versus just like when you see that squiggly thing that represents an integral, right, is a lot easier to intuit than just like the raw math of what's going on. Why can't I play?
We're talking about looking how these three quantities change over time, and these three quantities are all related. If I want to know, if I say that I have a function for an object's position, then these three are related very simply. The first derivative, if you remember your high school calculus, the first derivative of the position is the velocity, and the second derivative, right, of the position is the acceleration.
Oh no, I got that wrong, didn't I? Velocity is derived, yeah, no, didn't I? No. Yeah, velocity is derived from position. Acceleration is derived from velocity. I got that wrong. Position is the integral of velocity. Yeah, so I got it. I got the order reversed. Shame.
Okay, and so that is, like, again, these are just the fundamental equations that govern how things actually work, sort of in the simplified representation.
My short-term memory loss is that bad. I'm just gonna, chalk this up to dad brain. Actually, I actually don't remember what I said was which. Like. I don't remember if I said velocity was the integral or the derivative position, but looking at it now, the fact that he actually wrote it out, I can make sense of that.
That allows us to just consider entire collections of atoms, if you will, to act as one. And so it may look a little daunting because he's drawing these f of t's up here, and he's got all this stuff, and there's time, and I don't understand what's going on. This is getting confusing, but it's actually relatively straightforward, and I can kind of relate it back to what we're doing in the code relatively simply. We already have one of these things in the code, obviously, right? We already have position, because I just pointed that out to you. That's right here. That's our player P. And we know this is our update loop. This is how player P gets updated. What were we doing, right? We took the player position. We multiplied by however much time we wanted to advance the delta, the difference, like however, the motion, basically, that we want this guy to take. And we added that into wherever he already was, right? And so if you think about what that's doing, okay, yeah, again, going back to our sort of vector representation of things, if the guy was here, right, and this is my position. So this is my position right here. If the guy was here, what we're essentially doing is we're saying we have a direction that he's going to go, right? That's our D player right there. And then we're multiplying that direction by the time, by dt for frame. Now, why did I call it dt? Why did I call it dt? Well, it stood, and I didn't actually say this at the time because we weren't there yet. It stands for delta t. T, obviously, is time. Delta t means the difference in time, right? It's the difference in time between 2 points, last frame and now, or in our case, since we're doing it slightly differently, we're actually doing it the difference between the start of the frame and the end of the frame. We're like sort of thinking about it in that sense. So we're saying the frame, the stuff was here, and now it's going there, and while the frame is up on the screen, we're imagining the objects to move from one place to the other over that time step. So if we were going to do motion blur or something, it would be across that time step, if that makes sense. So there you go. So that's actually what we're talking about here, right? And that's what we're doing when we actually do this update. We're taking a direction, we're multiplying it by delta t, and that's how far we're moving him, right? Now remember, I believe we talked about this a little bit. No, I guess we didn't really talk about this too much. So I'll mention it today because this is actually relatively important. We talked about scalar multiples of vectors, right? We basically said that if I have a vector, I could multiply it by some scalar, like I've got a vector here, I could multiply it by, say, 2, and I would get a vector that's twice that length, pointing in the same direction, right? And what I don't think I ever actually said was you can consider vectors as having a magnitude, right? We could consider vectors as having a length, and we did a bunch of that stuff yesterday. Remember, we were doing the Pythagorean theorem and stuff, and we're looking at how long some of those vectors are. So basically, from here to the from the base to the tip of the vector, right? That's a particular length, and that we call that the magnitude of the vector, right? So you can think of vectors as having a direction, which is sort of the line along which they're pointing, and a magnitude. And that direction is actually signed because it's either pointing positively or negatively in that sense. And then the magnitude you can think of as how long it is in that direction, right? So that's just something to keep in mind. So again, what we were doing when we were actually computing the update for our guy is we were taking sort of a direction, a place, a sort of a line in which we wanted him to travel, which we had set up here using what keys were down. And then we said we're going to move him as far along that direction as there is time in the time step, right? However big the time step was, that's how far along the line we're going to move him. Now the time step, of course, is in seconds, and it's going to be some fraction. It's going to be 0.0 something seconds, right? 0.033 seconds or something like that, because we're at 30 frames a second, so the amount of time between 2 frames is a 30th of a second. So basically what we're doing is we're taking the vector and we're making it have magnitude 0.033 if the vector was unit magnitude. Now the vector isn't actually necessarily unit magnitude, although I think it always is. All right, yeah. So we always are actually setting that vector, you can see here, to be a length of 1, right? It's going to be 1, -1, -1, or 1. It's always got 1 as a magnitude. And in the case where we were going to move both axes at the same time, we solved the Pythagorean theorem to see what that distance should have been in order to reduce it down to being the same as it was here, which means this is actually also going to produce a vector of length 1, which is kind of amusing when I think about it. So yeah. Oh, okay. But we do one thing here, right? We've got one other thing in the mix. In fact, I think I'll move this down below here just to make clear. So then, what we do beyond that, now that we actually know, okay, that's how, we now have a vector that's sort of magnitude 1, we then said we have a speed we want the player to go at, which is going to be 2 meters per second, right? Because our world units are meters, and we're talking about how fast this player is going. 2 meters per second, or if I have the special magic button down, it's 10 meters per second. And then we were multiplying the vector by that. So we actually already did another magnitude scale here. We took a unit length vector, one that's only 1 unit long, and we multiplied it by this to get a vector which is that long. It's going to be a vector that's 2 units long or 10 units long, depending on how far, depending on whether that button was down, right? And then when we actually go to move the player, we multiply that total vector by which is this right here, by however much time we want to advance. So this is essentially, that means this vector, if you think about what its units are, this vector is the amount that the player would move in 1 second, because we're multiplying by fractions of a second, right? So what we're essentially doing here is this is meters per second, right? We're multiplying by seconds and just getting meters out, right? Again, dimensional analysis. So these are meters per second units, if that makes sense. This is in seconds, and so out comes meters per second. And again, we've kind of been sneaky about it here because we never really came right out and said it, but what we were basically doing is we were doing all that essentially with vector math. We were saying we want to make a vector that's going to represent his movement, and we want to represent the movement cleanly, so we can just say meters per second, which you'll note doesn't have a direction to it. This is just 10 meters per second in some direction. And we let the fact that we have a unit vector pointing in the correct direction tell us how to construct the motion in x and y that actually corresponds to this speed along that line, right? I know it's a little confusing, but I just thought I'd point that out just really briefly. Okay, so we can go over this again in the Q&A if it's complicated. I know there's a lot of concepts here, but point being, that's what's happening, right? We're basically taking a position where we're starting, where we've got a direction, and then we're trying to make the magnitude of our resulting vector that we're going to move by be proportional both to how much time has elapsed and how fast the player is going. So we have a speed in meters per second, we have a time in seconds, the seconds cross in dimensional analysis, remember, so they go away, and we're left with just the meters. We advance the guy by the meters, and again, it's all in vector, so it's got a direction, it knows what direction it's going, and it knows how far to go, and boom, we get to our new position. That's what we were already doing. Now, what is actually going on there, right? Well, we know that position is measured in meters. We already said that, right? We already said that position is in meters. Well, what is this meters per second, right? So we did seconds, we crossed out seconds, right? We basically said, let me write this equation actually explicitly over here. We actually said, right, we said we have delta t seconds times whatever our player motion is. So our player motion amount, motion or whatever you want to call it, meters per second, right? Like this. And I crossed out those seconds and I got meters. But what was this sort of motion meters per second weird value that we were multiplying here? We know this is a time step, right? We know delta t seconds is a time step. But what was this nonsense over here? Well, that's actually the velocity, right? Meters per second. It's how many meters somebody goes in a second. And that is exactly what we were doing right here. We were actually doing a velocity-based update of the position of our guy. We computed the velocity to be dplayer, which is either a 2 or 10 unit long vector pointing in the direction the player is going. We multiplied by the dpt per frame, which basically gave us how much to move the guy in position space for that time step. That's basically integration. We integrated a velocity up to a position, right? That's integration. Integration goes this direction, right? This is a high school calculus again. Integration goes up.
I did not take that in high school. I finished at pre-calculus. So yeah, I think I'm quite certain that I said it wrong, and I think it just might be because whenever I'm trying to think back to when I did finally take calculus, and I was like 23, and I think I actually just had the integral going down. I think I would have written this out in the opposite order. So I would have had, the integration down a position down here, and then the derivatives would have gone up. I can only assume that's why I would say the complete wrong thing, other than, me just not having looked at anything calculus related other than this guy's stuff in like nearly 10 years.
Derivative goes down, right? And so we've already performed an integration, you just didn't know we were performing it. And that's not really particularly surprising, because if you think about what happens here, right? If you want to integrate a very simple constant quantity, you just have some motion that's not at all dependent on time, right? If you just have to integrate 2 meters per second, right? Then obviously the integration for that, if you remember your high school calculus, is just multiplying by whatever the change is, right? Delta t is exactly how you would integrate that up to position, right? That is basically a discrete integration up to a position. Now I'm running out of space here on the board, which is unfortunate because I'd like to keep going, having these things around, but no, I can't. What can I say? So let's think about this a little more explicitly, right? Let's think about position, and that's my f of t. I've got velocity, which is my f prime of t, and I've got acceleration, which is my f double prime of t, right? Now, what, I'm just going to write down basically what you probably remember from your high school calculus class, and then I'll sort of come back to what I was saying just a few seconds ago and kind of try to tie it up a little bit just to make it a little more solid, right? So if I have some function of position, right? I don't know what we want to say that it is. I don't know. Let's say that we just had some function of position. So we have our f of t. That means we're going to plug into t. We want to get a position out. Whatever it is, right? I could say that that was something like 5 t squared, plus 2t plus 3, right? This is, again, standard old calculus stuff that you might see.
Let me see if I can do I don't know why I feel compelled to do this, but I just feel like I have to. So we're going to drop that constant 3, right? Because he's about to take the derivative of f of t here. And then we're going to have, what is it? It's going to be, we're going to take this exponent, we're going to knock this exponent off. And then I think we're going to have 10t plus 2. Is that right? We'll see if I'm right. That'll be f prime of t. It would give us, I think, well, would it? I don't know if you would actually. Yeah, I think it would be, right? 10t plus 2, and we drop that t. Drop the constant, drop this t, and then that would be our velocity, or f prime of t. In a textbook, right? And we all remember how you would do the derivatives, right? If you want to take the derivative of that function, you do this thing where you take the exponent of the variable, you multiply it by the front, and then you reduce it by 1, right? So you'd end up with 10t, right, plus, again, this one doesn't have 1, so this is just an exponent of 1, so it's just going to remain 2, and then reduce it by 1, that gets t to the 0th, which is nothing. And then this guy doesn't even have a variable, so he ends up getting knocked out entirely, so he's just gone. Oh my god, I was finally right about something. Yes! I wasn't humbled for the umpteenth time this week. Right? And so we end up with something like that, and that is the velocity of... I did it. I can do a basic high school calculus equation. I can't believe it. It's amazing. Yeah, this is just... Oh, God. This thing, right? Now, you may ask, like, I don't understand. What are we talking about here? And again, you can think of these just as we were... Just think of these exactly what we were doing here. Remember, we have the x and the y written out separately. Think of these as the x's and the y's written out separately. This is the x coordinate of our guy. We just had a function that we said, we said he was on rails. So as time increases, he's just at this x coordinate. We just compute it, and that's where he's at. And we want to know what the velocity is, right? So we want to know what the derivative is. We want to know how fast he's going. So this is our velocity. That's how fast he's going. That's how fast he's going in x, right? It's his meter per second. That's what that is. And then if he's going to take f double prime, right, that just leaves us with t. Our acceleration is, right, 10. Just a constant value of 10. Why do you gotta say it like that, devil? You don't appreciate the beauty of calculus, the wondrous observation of the universe that is mathematics and applied calculus? If we want to know his acceleration, we can take it again, right? We just go down one more time. And again, this guy drops out. This guy is... Oh, I did it again. I got it right. I got 2 things right this stream, and it only took half an hour. Moved completely, so we just left with 10, right? And that's just directly what the acceleration actually is, right? Now, what I hope you can see here is these relationships are actually very simple. And if, for example, right, I wanted to know I wanted to be able to do this discretely, right? Because what you can think about here is this is all well and good, but it presupposed that I could write an equation that's the location of my guy. But I can't write a location that's the equation of my guy. The user's like entering, commands and stuff. He's telling me where the guy moves every frame. It's changing and all this sort of stuff. So I don't have the luxury of just writing out some specific equation that says where the guy is for all the time in my game, for any time step, at the first second, third second, fifth second, whatever, right? So what I need to do is I need to move from sort of the way that you think about it in high school calculus class, which is perhaps not very useful, even though all the tools are there, right? I just need to start thinking about this in terms of doing it discretely, so that instead of actually trying to make a function, I'm just going to say we're going to discretize it down to one time step, right? And so if you think about it,
here's our game time again, like we always say. I've got time equals, this is frame 0, this is frame 1, this is frame 2, this is frame 3, this is frame 4, right? And so in time, in t, this is in frames, right? In t, we basically got time 0, time 0.033, repeating 0.066, so on, right? This is what the t variable is. If I was lucky enough to have somebody who was always moving based on just a fixed equation, right, I really wouldn't have any work to do. All I would do is just take that equation, and wherever I was in time, so I want to draw this frame, I just go, oh, 0.066, I plug it in here, and I get the x-coordinate out. Done, right? No problems. But we don't have that luxury because the user is inputting stuff and all this sort of thing. And so there is no constant equation that we can just use all the time that will give us back the location of the guy. So what we need to do instead is switch to something where we're essentially discretizing these equations of motion and pretending that the equations of motion are essentially constant over the time step. Meaning we're pretending that the guy is just going to move in a line over the time step, and you know, the time step's going to be so short that he appears to like curve and do stuff, right, on when he's actually, when you actually see him, he appears to be changing direction and doing all these things because over time you're changing your inputs and all this stuff. But really, in any given time step, what we want to do is discretize it down so that we're basically just taking the input that you gave and applying some piecewise function, the function that only is going to operate over that time step. And then on the next frame, we will essentially be using a different function, right, which is a different, responds to the keys differently, right? And when I say function, I don't really mean much of a function at all. I'm just talking about a very simple function that's like we already had, where we have a vector direction, and we're going to basically pretend that the guy is moving along that vector direction by delta t, right, or something like that. So very, very simple version of the function. It's nothing complicated, nothing too interesting, right? So in order to discretize this, I guess what I would say is, so you know, hopefully people are comfortable with how to take a derivative and what we did here. And basically what we want to do is say, okay, let's just assume, right, that at every frame, we're going to start down here with a constant acceleration, and then we'll just integrate it up, right, to get our velocity and our position. And we don't care about the fact that, you know, each time we integrate it up, we're essentially creating a totally different function with different coefficients, right? Because if this frame it's 10 and the next frame it's -5, we're going to get completely different values when we do the integration up, right? But we don't care about that. Like I said, we're just going to say for each frame, we're going to pretend that we have a different, essentially a different set of coefficients, if you will, in our function here, right? So really, there isn't a whole lot to this. We already did the work. You can read it right off of here, even if you don't know how to integrate. If you just know how to take derivatives, you've already got the answer, like, because we're looking at the answer right here. If we wanted to say we want a particular acceleration on every frame, well, here is that acceleration, right? It's 10. Right? That's the constant acceleration. So let's just replace that constant acceleration, right, with whatever we want the acceleration to be, a, whatever we compute it to be, okay? We then say, all right, our velocity is the first integration up from that. The 10, remember, comes from here, so this is actually going to be a, and it's a times rt, right? It's times whatever the time value actually is. And then we do plus 2. What is that 2, right? What does that 2 actually mean? Well, the 2 is essentially the existing velocity, right? It's saying this was the part that accounted for the acceleration, the change in the velocity, right? Because it's multiplied by t, so over time this is change in our velocity. This is the constant velocity. So this is whatever velocity was on the last frame. This is what we're coming into it with, right? So this is just our v. That's our v term. So at plus v is actually the term that we want to use for our velocity, right? And then finally, when we get up here, you can see that we get integrated up one more time. This plus right here is just the existing position of the guy, right? This, we're adding a new position for the guy. We're taking his old position and updating it. So this constant that was in here before is just wherever he was, right? There's the p, right? This guy right here is the velocity again, right? That 2, that was the 2 from right here, right? So that's just the v. And then here you can actually see, and again, this is why I say even if you don't remember how to do integration, you can cheat it by just doing the derivative and then doing it backwards. Remember how we got this? We did 2 times 5, right, equals the 10. So all we have to do is divide the a by 2 to do our final integration, right? That's why this was 5 instead of 10, right? So instead, we just have a over 2 plus v plus p, right? So what does that actually give us? That actually gives us the final, if I just read these off and get rid of the scribbles, right? That basically gives us that our top equation for motion is, you know, 1/2 a times t squared, which is this term right here, right? Plus v times t plus the old position, right? So whatever the old position was, yeah? And again, this v is actually the old velocity as well. The velocity, right, whatever, and so this is our new position. This is our, and a lot of times we do p prime for that, so you don't have to keep writing old. You just assume that these were the old ones. P prime is the new position, so we just have p prime equals 1/2 at squared plus vt plus p, right? And so if I want to know p double prime or base...
It's so easy to take that simple little calculation based on the inputs that you got, you know, your dt, and then, you know, you have your, whatever your acceleration constant is, and then you got the 1/2, like how much goes into just being able to nicely articulate it that way and just have that sit around in your code forever, and then you forget why it's there. You just go, you know, this is how you get the new position. You just, like, I couldn't even articulate it, but now I think this is going to settle in a little bit better this time. Devil asked, when are we getting to the chain product and power rules? You know, we're only going to touch what needs to be touched to actually work on the game, right? And then I guess we can just throw the rest of it away, unless, you know, whatever kind of game that we're trying to make is specific. Like, I'm, you know, trying to think of what kind of game would force you to get really. I mean, like I guess I don't know if this is actually a good example, but like a Kerbal Space Program where you have like a ton of different things going on that are physicsy related, right? Or you'd start to care about. But I don't even know if that's true. Like it's all going to be dependent. Like, yeah, I don't know. I wish I had somebody more experienced on tap in this arena to talk to, and there are actually people out there that like hang out in forums and discords and stuff like that you can talk to this stuff about. And maybe I keep joining new discords depending on where my area of interest takes me. Like I'm now part of this graphics programming discord that I found, but maybe there's like this. I mean, of course there is a physics discord somewhere. I gotta go and join that and and get an understanding of all the different kinds of math that could come up in something that is like physicsy related and therefore would impact your game. But maybe there's like a game mechanic reason, that isn't really necessarily physics related that would cause you to care about more obtuse math concepts that you wouldn't normally see crop up in a game.
The new velocity, right, v prime, then that's just this equation. That's at plus v, and then finally, if I want to know the acceleration, it's just prescribed. So basically, there is no new acceleration because we never saved the acceleration. So there's just acceleration that we specify, and now we can specify whatever acceleration we want, and we can compute any of the quantities that we actually wanted to compute. Now, you will notice that these things basically don't really imply all that much more stuff than what we were already doing, right? Essentially, we just didn't have these terms, okay? We had this. That's all we had, right? Does that make sense? Now, I haven't really talked about the delta t part, but just bear with me for a second. There's a lot of stuff to cover here, so I'm trying to make it, let's see how much we got. Oh, we're tight on time. All right, so if you take a look here, we already had exactly that top equation minus the acceleration, right? We just didn't have an acceleration in there. We had whatever the dt was times the velocity that we wanted the guy to go at, right? And so that was this. That's the velocity times the time plus the old position. Velocity times the time plus the old position, right? So we're already computing part of this equation, and your intuition, when you're writing a game code, even if you didn't know any of this stuff, is to write that, right? That's what you would write, and that's what we did write. So really the only thing we have to start doing now is thinking about this other part that's maybe not so intuitive, which is that there's another quantity here which gets accumulated into that velocity. So the velocity is now something that actually needs to be stored from frame to frame so that we know how fast something was going, so that we can update it with our acceleration every frame, and then integrate it into what we think the position should be, and so on. And similarly, in order to properly account for the effect that the acceleration has, we want to put it in this equation as well. We want to put it in this part of the equation here, the 1/2 at squared, to account for the effect that the acceleration has over this time step as well, right? Because without this, essentially what would happen is we would be assuming that acceleration was not actually continuously happening over the course of the frame. Now, we could argue which one of those we'd rather have, whether we want to have an instantaneous acceleration, which is what would happen if we didn't do it this way, right? Let me explain this in a little more detail. There's two ways we could have chosen to program this. One is to do this step first, right, and use v prime here. Okay, do you see what that would do? That would still get us a t squared for our evaluation because basically this at is baked into here, right? This term, right, which was normally vt, which is the old velocity times time, which just says that velocity is carrying through from whatever it previously was, it's carrying through this frame, right? If I change that to v prime t, well, v prime t is this, right? So if I multiply that out, I'd get at squared plus vt, which is close to this, but not quite because there's that 1/2 in there. So essentially what happens is that 1/2 is counting for the fact that the acceleration is being evenly distributed across the time step, not instantaneously applied at the beginning of the frame. And so it is technically more accurate to do it that way in terms of what you were trying to actually simulate. But what we have to also acknowledge here, for anyone who wants to write it the more simplistic way of just doing this and then using v prime in here, is that we're going to hack all these variables anyway. We're going to tune all these variables to be stuff that feels good to play. And so at the end of the day, it's hard to get too pedantic about it and go, well, you got to do your 1/2 at squared, and if you don't do 1/2, you're not doing it right or whatever. It's hard to to really make that argument, right? But what I will say is, if you want to do real physics at some point, you need to start sweating those kind of details, because things start to get much more important when you're not hacking a bunch of variables to just make the guy feel good or whatever, and you want to actually try and get realistic, believable behaviors out of certain physical properties and that sort of stuff. So it's good to know.
The thing that's weird about it, though, is like, just because your physics, it's a hard thing to even begin to untangle inside of my head, but I'm trying, based off of the notion of what he's driving at, is that if you're trying to do something that is more realistic, you're going to have to care a lot more about getting this part right, because just because the equation is the equation of acceleration and velocity and calculating the position from those, just because that's in your code, like even if the outcome in the game that you're making is like as realistic as you can make it as far as like how the actual calculations are being made. It doesn't actually feel, it might not even feel realistic. Like things might feel really floaty, even if like on paper, if you look at it on paper, things might feel wrong because of the way things look, right? I guess that's what I'm thinking of. All these things impact each other, and it's hard to know where to even begin to solve that. But I don't aspire to make a super physically realistic game, but it could just be a good learning experience to start learning parts about that, because it can tie back and inform other things, right?
What the equations are and how they work before you start
other things, meaning specifically if you're not trying to make a game that is super realistic, but you want to have, you know, these realistic qualities to some aspect of the gameplay. Like I'm imagining, and this is just a dumb example I pulled out of my butt just now, but like if you're like making a platformer and you want to create a different sensation for the player when they're jumping on like a solid platform, like think about like a regular Mario platform or something, but then they're jumping on like clouds that are kind of like floaty. You would expect those to kind of react a certain way, right? A game of billiards, Devil said, could have a bunch of physics. Yeah, like something that simple of a game, if you wanted it to be, yeah, no, that's a really good point. Like you could do something really simple to try and get a sense for what it's like to try and make a game that's more realistic. And then you're not, I imagine, maybe this is incorrect, but I would imagine that's a good deal simpler than, say, like a flight simulator game, where a flight simulator, if you want it to be as realistic as possible, like you'd have to keep in mind all of these aspects of like, what is the actual aircraft you're flying, like a helicopter versus and I don't even know if Flight Simulator has helicopters. I would assume they've added helicopters by now. It's been so long since I've touched a Flight Simulator game. But, think about like the difference of what it feels like to fly like a Cessna 152 or whatever versus like a jumbo jet or something. Like it... I'm thinking back to those moments of like picking all the. I think I just always wanted to pick whatever like the fastest thing was. So whatever, like it would have been like a Learjet or something, playing Flight Simulator growing up, because my dad, he actually had like the yoke because he was a pilot, and so I would basically just like pick the fastest plane and then try and crash it as soon as I took off. Like I just wanted to go fast and then crash in a really dramatic way, and I didn't really think that much more deeply about it. I wanted cool crash physics, and of course in those really early Flight Simulator games you wouldn't get cool crash physics. Things wouldn't explode. I don't even know what they do today, but you would basically just like kind of get stuck into the hillside, and then maybe there's like a little crash or explosion effect that plays, but it's very unceremonious. You basically get stuck like a paper airplane or something flying into a dirt hill or something in those earlier Flight Simulator games, at least from what I remember.
Them so that you don't end up at a limit where you can't get past something and you can't make something feel or work right because you've forgotten all this stuff and been sloppy, right? So it's good to know the rules and then break them, not just sort of go willy-nilly about it. So I just want to kind of point that out. Okay, so finally, really quickly, and maybe we'll have to go over this again tomorrow because there's a lot. I had to talk a lot to sort of talk some of these things out, and I feel like a lot of it's just very detailed and tough perhaps to absorb. But anyway, what I did want to say is, where does delta t come in, right? Because those functions that I wrote over there, they were continuous functions. So when I said 1/2 at squared, right, plus vt plus p prime, when I said that, that's just a function where you plug in a t, right? That's a function where I just plug in some t value and I get the position straight out, right? So what's going on here? And the answer is, well, remember, what I said we were going to do is treat these functions as if they only exist for the time step, right? So effectively what we're doing is every frame we're creating a new equation of motion where we specify a new acceleration, integrate it up twice to get our equation of motion that will store our new velocity and our new position, right? And so really this is f of 0 at the beginning of a frame, and f of delta t, however much the frame time is here. Then on the next frame, we're going to do the exact same thing again. Pretend this is f of 0 and pretend this is f of delta t. And what do we want to know? We want to know where the guy would be at the end of the frame, right? So if we want to know where the guy would be at the end of the frame, well, that's delta t. That's what we would plug in. So we plug in delta t to our function, delta t, and that's why everything is in terms of delta t. It's because really delta t is the time at which we want to know. If we wanted to know where the guy was at the beginning of the frame, we could still use the same equation. It's just all of these terms drop out, and we just get p prime, right? T squared, if delta t, if we're plugging in 0 for this, and we're saying f of 0, that drops out because obviously 1/2 a0 is 0. Same thing with vt. If t is 0, the v drops out, and we're just left with p1, which is exactly what we would expect. If we haven't gone any farther, if we haven't gone anywhere in time, we would expect the guy to be wherever he was at the end of the last frame, which is p prime, right? So again, what we're trying to do here is we're just trying to put together piecewise functions that get us from one frame to the next, and we restart the function at the beginning of every frame, right? So it goes from 0 to delta t, 0 to delta t, 0 to delta t, right? Now that's not to say that we couldn't have some object that does have a function that it uses across many frames. That's totally something we could do if we wanted to. It's just that's not something that's particularly useful for a guy who's under player control, because when you're under player control, you really do restart your acceleration every frame, and you're getting basically a totally different function. It's not some smooth continuous function that can be mathematically analyzed in that way. It's piecewise, is what it's called, right? It's a piecewise function, which means, you know, a normal smooth continuous function looks like this kind of thing. A piecewise function is one that's like a, you know, that kind of thing, right? And it doesn't actually have to be lines in between there. It could be, you know, like this. It could have curves, but then the curves have sharp bend points, right? And those pieces, that's why they call it piecewise, because there's basically, it's pieces, right? Little individual segments. And basically that's what we're doing with our stuff now. Okay, so very quickly, we don't have very much time left, obviously, because I had to sort of yammer on at you about those things. What did I actually need there? Well, remember, I need a velocity. I need to store a velocity, right? I need to store, and I usually use d, like that's what I use dd to denote accelerations. I use d to denote, well, I use dd for second derivative, d for first derivative, right? So one of the things I need to do now is we were just working with the velocity that was just only existed on that frame. We need to start storing that velocity, because remember, v, the old v came into play there, the old velocity, so we need to start storing that from frame to frame. And we can assume it starts at 0. That's totally fine, because obviously we know that the guy will not be moving at startup. He's just staying where he is. And so then what I need to do in here is I need to start thinking about this in terms of his acceleration, not his velocity change. So what I'm going to do instead here is say that this d player, right, that we're actually doing here is actually dd, right? So d player is going to become the dd player. So that's actually his second derivative of his position, right? And so now what I'm going to do, I obviously still want to compute, I want to compute those equations of motion the way.
For some reason, maybe it's just because I've watched that lecture twice now, but this time around, I feel much better about calling it dd, just because I paid a little bit more attention to the point about it, you know, being the derivative of the derivative of the player's position, whereas before I just wanted to call it acceleration. But I'm pretty comfortable with this at this point. So, like he's saying, we're going to be changing the player's acceleration here, so just got to update all those places where we were talking about the velocity before, right?
That I said I wanted to on the thing. So again, we have, let me write them out for you again. So again, we have 1/2 at squared, right, plus vt plus old prop p, right? That's our equation for, I'm sorry, here we go. That's our new position, right? And we have, for our second derivative, right, or our velocity, our new velocity, we said that was just going to be at plus the old velocity. And similarly, the acceleration, right, is just specified. We don't have to do anything about that. We're just specifying it. The user is basically, this is coming from the d-pad, right? The user is saying what that acceleration is. Okay. So we want to actually just compute that, not too hard. 1/2, right, a times t squared. So I'll go ahead and say square. We need to write that. We haven't written that yet. So that's literally 1/2 at squared, right? I'm really just literally typing it in. Then I want to do the same thing for the vt, right, the vt term. So that's here is his velocity. His velocity is the game state d player. There we go. Times that delta. There's t. And then I just need to use his old position, which for, you know, just to make it totally clear, I'll put it in there and change this to an equals. So that way it looks exactly like the equation we wrote. 1/2 at squared times.
Well, I was hoping that I could just reach in and grab a square proc from the math package. Math package? Well, if I could at least talk right, that would be good. We get a lot of square root stuff, but no squaring. So maybe I would just have to define that sort of thing myself. I don't really care. It's just if I can use something that's built into Odin, I would prefer to use that. Math big rears its head again. I don't know. Who cares? We'll just do it ourselves. So we'll say square our dt for frame, and that gets added to game state delta player p. Did I call that delta player p or delta player? What did he call it? He did call it d player p. Okay, so he just hadn't had a chance to finish writing that out. Plus or times input dt for frame plus the new player p, or would that be the old player p? Because we haven't. Where did we get that out? We're getting that out right now. Yeah. I guess it doesn't matter if you're calculating, if you're adding the old game state player P offset or the new one, because we haven't changed it. So it's the same value that it was before. So let me see if I can split this up so that we actually get each line is like one piece of that equation. I think that looks like that. So we just need our square proc here next. Is that what he did? That looks like it's what he did. Yep. Yep.
Times plus VT plus the old position, right? So that's the update right there, very simple. And the other thing I can then do is say I'm going to change his velocity as well. And so his velocity, and there's a couple of things we want to actually talk about here. So the velocity update is going to get a little fancier than this potentially because of when the player is colliding with things. But for right now, let's ignore that so that we can, because we don't have a lot of time, like I said. So we'll kind of do a more straightforward version. So to update that velocity, to give him his new velocity, again, it's really simple. It's just the AT plus V. And so I literally type that in. There's my A, right?
What was it? AT. So DD players A times T plus the offset. Was that right? What did he say it was?
V. And so I literally type that in. Again, it's really simple. It's just the AT plus V.
Plus the velocity. Okay, so new player P dot D player P, right? What is it saying? Do these values not play nicely? Oh, game state. Okay, because yeah, that's off of the game state, not the player's position. Got it.
And so I literally type that in. There's my A, right? There's my T, right? And then I need my old V, which is this right there. Okay. And so that's pretty straightforward. There really isn't all that much to it. That is the entirety of the actual code that we would need to do the update. So all we really need to do now is actually create that DD player correctly. And so we could probably just leave it as it is right now, which is to say that he accelerates at 10 meters per second squared now, right? Because again, this is an acceleration, so it is now no longer meters per second, it's meters per second squared. That is just sort of taking the derivative in time space, right? Because remember, T, we are not taking, it's important to remember, we're not taking a spatial derivative. We're taking a derivative with respect to time. And so basically we start off in meters, we get meters per second, and then we end up with meters per second squared all the way at the bottom. Time is the thing that's increasing in order of magnitude in power here as we take that derivative. We are never actually changing the meters because we're not taking a spatial derivative. We're not trying to ask how these equations change when we move around. We're trying to ask how we move around based on changes in time. And so that is why you notice the meters doesn't change. That's kind of a topic for another day, but point being, just thought I'd throw that in. Anyway, so we got our acceleration now, and in theory, I think actually that was literally all the code.
Var to the 2 should be equivalent to square. And I can even use floating numbers. So are you telling me right now, did you just find this out looking at Odin's documentation? Are you a sweetheart? Did you do something sweet for me? I can just do this. Or are you saying that's the way it should be, even if that's not the way it is? Because right now it's telling me expected a paren and got an integer. Is it because, wait, what did it expect? It is expected a comma here. Google AI told you when you looked it up. Well, how could AI possibly be wrong? You know, we must be the wrong ones. I guess I could just see. I have the Odin Discord open over here. I'm just gonna do a quick search. Square power. Okay, that's not helpful. Square a variable. How to square. I don't know how to look this up correctly. Nothing's working. It just seems like something that should be like a parametric polymorphic proc that's just called square. Let's go back to the home here. Square. SC square. Just take another look and see if we get anything. Raylib gen image gradient square. Distance squared. Lots of Vulkan DirectX stuff. Well, maybe I need a space between the caret. Yeah, maybe. I'll happily do it this way if we can figure that out. Maybe in the overview. Or maybe power is power of 2. Power of 2. Power state. Or just pow. CPow. Int pow. Math big int pow. Is power of 2. Internal pow. Pow, 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 pow. Utilizing the power of struct of arrays. Pow. If I just look up caret here, we're gonna have a whole bunch of stuff to surf through. That's a dereferencing thing. Yeah. Like if I look at this, if I think about what this is doing, right? This is dereferencing syntax in Odin, but this is just a value. This is just a float that we're storing in the game's input. So I think the compiler thinks that I'm trying to dereference this, but then there's just this 2 floating after it, you know? Hello, Gunther. Try ** like Python. Yeah, something tells me Ginger Bill didn't give us a ** operator. It's actually complaining about 1 star. What's that about? Shouldn't you be complaining about both my stars? Anyway, yeah, I don't know. We'll come back to it. If there's a way to do this without implementing it myself, then that's the way I would prefer to do it, because what's the point in doing something like that myself? In my eyes, anyway. Because it's just such a simple thing. I'd rather use the built-in thing that, like, if another hypothetical Odin programmer was to ever look at this and be like, oh, I know what that does, you know. Then again, it's a square proc. Like, how much intuition do you need to be able to understand that that's what you're doing? Let's just move on.
That we would need to write to give our guy momentum, but we need to write that square function. So in my handmade math, I'm going to go in here as well and add a little squaring function. A squaring function is just one that takes its value and returns it squared. The simplest possible thing you could imagine, right? A times A, and there we go. So that's just a way. And why do you do that? Why not just write A times A? Well, it's a little bit easier. This might.
So he's going to do it using a float. I'm going to be terribly clever here and use, where was that? Up here. I actually don't even need to use parametric polymorphism up here, because it turns out there is some built-in kilobyte and megabyte and gigabyte and terabyte proc or something like that in one of Odin's packages, but I've left it in here because I've been too lazy to change it, but that's something that I intend to change. And we use these to like allocate, what is it? It's like a gigabyte for the game memory or something like that. But anyway, I can look at those and know how to implement this. So I've got my value here, my value A, and it's going to be, well, should I just call it value? That's what I'm doing for these. I think he defines macros for these kilobytes, megabytes, gigabytes, etc. Procs, but so he doesn't have to. Maybe he just calls it N or something. I don't know. It doesn't matter. We're going to return whatever that type is. If I can do that properly. And then our result is going to be value times value and then return result. I guess I just don't understand why that wouldn't be. Like, there's probably something else I could do here to make sure that this is always going to be some kind of number, right? Whether it's a float or an int, but I think that works fine.
Be a whole expression sometime, right? Like, right, or something.
And I guess I should make sure that that actually got rid of that. Try and build. Why not? I'm afraid to run it because I feel like something will break.
Something like that, and you don't want to have to type that out twice because you might make mistakes, so it's nice to have a little squaring function that you can just use to save on the typing. Oops, that's D player P, and there we go. So I believe our guy, we probably have too slow of acceleration now. I don't know if we do or not. Oh, no, there we go. So basically our guy now has momentum, and he behaves exactly as you expect, kind of like, for lack of a better...
I shouldn't have been afraid. I should have just gone for it. Let's see if we run. See if we can glide around like Casey. Oh, God. Something's gone terribly wrong. Try it again and see what happens. Yeah, well, something's very wrong because where is the tile room that we're supposed to start off in? So clearly I did something wrong here. Not sure what yet. He did change all of that. Well, actually, yeah, no. So he modifies the DD player values according to the direction that we're needing to go in. Oh, does this work that way in Odin? I never even bothered to see if that works, but I don't see any good reason why I shouldn't. So we can just multiply the player acceleration vector by that, what is that, the square root of 2 or 1? I can't remember. We calculated that yesterday. Yeah, I think that's the square root of 1, right? Or maybe it's the square root of 2 scaled for like the unit length vector. I'm probably saying that wrong. But so we have our player speed as 2, and it's going to be 10 if we press the arrow key. Nothing's different about that. We want to modify the acceleration by the player's speed then, after we've decided what direction we're going in. And new player P is coming off of the game state player P. I see. This should not be a plus equals, which makes sense because this is the formula. We don't want to add to that offset. So it's almost like it probably shot me off into, like, in the first frame, shot us off into some place that we should not be in. Yeah, that was the only issue. So we can glide. I can skate. But it's, we're pretty sticky because we're getting caught on those walls. And it's just, it's so floaty that I think what he's going to do next, if I'm not mistaken, is modify those, these constants here, because this doesn't work for the acceleration. I think we need to bump that up maybe. Google AI lied to me. I shall remember this during the Robo War. Well, I'm sure it's not the first time, and it definitely won't be the last. But yeah, arm up. You know, it's going to be us versus them eventually.
Squaring function that you can just use to save on the typing. Oops, that's D player P. And there we go. So I believe our guy, we probably have too slow of acceleration now. I don't know if we do or not. Oh, no, there we go. So basically our guy now has momentum, and he behaves exactly as you expect, kind of like, for lack of a better term, like a hockey skater, right? Because remember, we've done no friction on this guy. So now he's essentially, you know, he's an asteroids guy. He's floating in space. He has no particular friction. But as you can see how trivial that was, and now he behaves exactly as you would expect a physical object with no friction to behave, just because we've spent the, you know, what is it, 5 seconds? I mean, I had to explain it to you for 45 minutes, but once you actually know what it is, you saw how trivial that was to type in, right? Now we've got the correct equations of motions for the guy, and it already feels kind of fun to drive him around. This is kind of ridiculous. And so now you can actually see already the thing I was talking about when I said we have some decisions and some interesting stuff we have to think about in terms of his velocity. When he comes in here and he sticks on that wall, right, our collision detector isn't letting him go through the wall, which is good. But we're not changing his velocity to be 0. We're just storing his velocity as if it's still fully accelerated in that, fully going that direction. Which means if I push the back direction, I have to push for a while to accelerate him up, right? And we could actually, if we wanted to, we could probably do something where we actually showed what his velocity was. Maybe that'd be a good idea to do in sort of quickly at the end of the stream here. And so what we probably want to do, right, because that doesn't feel very good for the player to get stuck against the wall, what we probably want to do very soon, and I don't know if it's going to be tonight because we're mostly out of time, but we want to start thinking about things like, obviously when we do the friction and stuff, we also want to think about things like updating velocity so that the velocity is actually what his velocity turns out to be after collision detection is done, stopping him when he runs into walls and stuff, because that seems like a much saner thing for the player to deal with instead of having this hidden pretend velocity that it doesn't really represent the velocity of the sprite on the screen, right? So that's it. That's really all there is to that. So now, if we wanted to, right, we could do something where we introduce some kind of friction as well to the dude, right? So
I totally forgot about friction. How could I forget about friction? It's such an important part of life, and how everything works. So there's that, and then like actually I don't know. Well, I do think that this acceleration isn't quite right. I mean, I guess I could always just play with it and then see what happens, just to satisfy my own curiosity. Probably just zip. Yeah, so I can move a lot more quickly, but it's so janky now because, like you were saying, that acceleration doesn't change after we get stuck on the wall. So now we're just kind of forever going in the wrong direction, and it's impossible to reconcile it.
if we wanted to, right, we could say, as he's running around, he gets some kind of a friction that's based on his velocity, right? And I remember we mentioned drag as well was another thing based on the velocity. And so I don't want to try to get into ordinary differential equations, obviously at this point, especially not with only like 10 minutes left in the stream. But if we wanted to right now, we could totally make it so that this guy actually had some friction by doing a sort of like approximated friction that doesn't actually quite do exactly the right thing. So I'm going to go ahead and set our loop live code editing up here. I'm going to have him kind of go this way, and then come this way, and then come this way again, like so, and then have that go, right? So I'm going to let that guy run there while we make our modifications. I'm going to go ahead and set him up over here, and then I'm going to open.
Gotta get myself set up to do the same thing. Haven't done too much of this. Whoops. On, where's my XZ? Well, I guess it probably wiped it out because I was in the middle of building. Let's rebuild it. Now we can run. And go ahead and get down here to the middle. Come on. We can do this. What? 3D viewer, what are you doing? Go away. You. Okay. Try that again. Start the loop. Kind of glide this way. And then glide back. Now we're looping. And I can stay on top of where Casey is in the code. Where am I? I've got so many windows now. And it's confusing because I've got OBS showing me the game, my game that's looping. I see my game, and I also see Casey's game. It's like Handmade Hero ception over here.
Open the window. I'm going to go ahead and do something I haven't done before, which is delete this window, and then actually kind of come over here and do that. All right. So here we go. So now what we should be able to do, right, is we can see that he's really swimmy. Like you can see how swimmy it is for me when I was controlling him. He kind of swims back and forth. And so I want to go ahead and add some kind of a function in here that's going to reduce his speed based on how fast he's going. So the faster he goes, the more it will push back against him. So like a friction force or a drag force, that sort of thing. And so again, I can't quite do this exactly correctly because we're going to need ordinary differential equations if we actually want to make something behave properly, but for now we can hack something in. And so I will say, oh, and you know what? We did fix the diagonal will be faster problem. We just didn't quite do it the way that we said we were going to do it. We'll do that eventually. Anyway, so to do ODE here. And so maybe we'll talk about that soon. But anyway, so what I want to do here is I want to say, okay, let's apply that fiction force. Now, I know how fast he was going on the last frame, obviously, and I also know how fast he's going on this frame. And so the question is, I guess, which exactly one do I want to use? And this is where, if you were using ODE, it would be correct, but we're not actually going to do that. We're going to do the hacky version. So I guess I'm going to use the old one, the one from last frame. So what I want to say is his velocity, I'm going to basically say his acceleration. You know what? I shouldn't do this here. I can just put it, I'll just pack that in acceleration. I'm going to say that there's another force acting on him. So basically his DD player, right, his acceleration. I'm going to go ahead and say I want to add into that acceleration right here. I want to add in a force that's going to counteract his velocity. So basically, I'll take whatever his velocity is, and I'm going to, say that he's going to accelerate in the opposite direction of whatever that velocity is. And for right now, let's even say that it's the full magnitude of whatever the velocity is. So you remember, this is our acceleration. So I'm just adding in an acceleration that's in the opposite direction of the direction he's moving, right? And so I'm going to save that, and we'll go ahead and compile that. I don't know why it decided to open that window. That's probably the least useful thing it could have done. There we go. So that looks a little too strong, right? As you can kind of see when you're looking at how he's going, it just looks a little bit too strong. So maybe I'll chop that down a little bit. Let's say 0.5, right? That looks a little bit better. You can kind of see, right? He can do his turn pretty good now, right? So that seems like a pretty reasonable coefficient to use there. I don't know. Let me jump back in and actually drive him around. Yeah. Yeah, that feels pretty good. Yeah, that's not bad. Now I feel like he's still a little sluggish, though. So I kind of feel like I want him to be a little bit. I think maybe this acceleration is a little too slow. So I'm going to jack that acceleration up a bit, and then maybe I can make this guy a little bit higher. Let's find out. Oops.
Aha, my intuition was right. Crank that up and rebuild. That maybe still seems a bit slow, but certainly easier to control. Now, like, there's actually something gamey going on here, which is that I have to almost skate properly to be able to correctly get into the next room. And, like, I'm imagining monsters shooting things at me now as I try to get through the next room. And maybe I've got like little fireballs that I'm throwing at other monsters to clear the path or whatever. The scale is wrong, which I think people start bothering him about because our hero is taller than these trees, but that's neither here nor there.
So you can kind of see that it even starts to look better, right, as you're doing that. And now I can make this dude a little bit stiffer as well, right? He can sort of be a little bit higher because now I've got more acceleration to counteract it, right? Yeah, so it's feeling a little bit better. It's still a little bit, and again, the higher I crank these two values, the stiffer that, so the more that there's a counteracting force and the more that the acceleration pushes against it, the stiffer that return to zero is, essentially, if that makes sense. So if I crank this up pretty darn high, right, and then did that maybe, I don't know, I'm just totally playing around with this just to see. You can see that he gets a nice fast stop there, right? I think I'm gonna give him even a little bit faster than that. So let's go ahead and jack that to 2, right? This is why I said we're totally gonna just write whatever random numbers we want in here as we tune it. So you can kind of see he's already starting to feel a little bit better in terms of that that sort of stopping behavior. I'm going to give him maybe 1.5 as the jackpot for tonight. Again, we don't really want to spend too much time on this because we're going to change a bunch of stuff. So now he feels pretty nice. Like I could see playing a game with that behavior, right? I could see that being just enough swimminess to feel good, but not too much. It might be still a little bit, there's a lot of things I'm going to want to do to this eventually. Let's put it that way. But for now, that's certainly fine. And of course, now I can sort of get him as he goes through here. Now, the other thing is I can also still keep my acceleration key, I suppose. I can make it so that, he gets a nice big speed boost. Whee! And of course, since we did all that through the acceleration, that even keeps his momentum and everything, which is kind of nice, right? Yeah. So it's all good. We still haven't fixed the collision detection. The collision detection is still a mess, so that's no good. But wait, why is our, oh, there we go. I was like, are we not, I thought maybe I broke something because he wasn't walking off the screen there, but all right, there we go. Yeah, so that's pretty good. All right, so I think that's good enough for today. Obviously, we've got a lot of stuff that we'd want to do to make this more interesting, and so I think maybe, but that's the basics of the equations of motion, and I think they are relatively straightforward when you start playing with them, certainly. We'll continue to talk about them more as we go. Now, one thing I did want to mention just really quickly that sort of kind of came up of motion. We'll continue to talk about them more as we go. Now, one thing I did want to mention.
So we did crank that all the way up to 50, but I feel like this isn't working for me for some reason. Oh, there it goes. I guess I just didn't save properly. So, yeah, not getting stuck on the walls just because it's easier to control. Not just... Like, it was like I was accelerating so fast before without any drag that he was just teleporting. He was so quick. And then teleporting into getting stuck on different random parts of the wall. It's like now I could imagine, like, if we just had like a constant, you know, gravity pulling us down, now we can just make, you know, Flappy Bird, but it's Flappy Hero, right? We just need a bunch of pipes or whatever, and then a little score counter that shows, you know, how long you've survived the pipes. Maybe it wouldn't be pipes, it would be whatever is deadly to the hero here, right? But we could certainly do that. Like Devil was saying yesterday, we could scrap all these tile rooms. We'd still use tiles, I guess, but they'd be, you know, big, scary, pointy. Maybe we could render it as like a triangle at the top. Just a bunch of spikes that he has to like glide over the top of. I don't know.
Mention just really quickly that sort of kind of came up at the end there, and I just don't feel like I really set it up enough for you to make it interesting. Here is, again, why vectors are so darn nice, and why I said I wanted to get a little simple vector struct in there for us to work with before we actually did any real player movement code or anything. You notice how easy it was for me to slam this correction in here, right? To just say, I want something that's going to be a friction force that acts against the player's motion direction. Well, before, we only had, you know, when this was all doing X's and Y's explicitly, it would have been much harder for me to start thinking about, okay, there's two different directions that are happening. One is the direction of motion. The other one is the direction that's the opposite of the direction of the velocity. Like, all of that, just totally I didn't even have to think about, because I can just go, this is an acceleration that has a direction. It's a vector. It knows directions already. So I can go ahead and just add more vectors in here, and it will automatically figure out what the new composite direction is, given the fact that it was adding two different corrections in for the acceleration, one that's about what the user's pushing and one that's about the friction. And it kind of just allows you to sort of smush all this stuff together. Vectors allow you to keep like adding that stuff in there. And so again, it's really nice because I can basically say, okay, I've got my acceleration for the player. I started out having the direction that the person was pushing, but then I added the sort of the force that was counteracting some velocity I already had, and that gave me a new vector. And then I did some other stuff like with the collision, which trimmed it down to here or whatever. And the vectors just store all that and track all that really nicely. And the fundamental operations on them look intuitive. Like, hey, look, I'm adding the negative of his velocity, which acts against his velocity, right? It does exactly what you would think it would do. And so vectors just really help you here, because if we did all this in scalar, it would just get so intractable so fast, and we'd have X's and Y's all over the place, and we were like, ah, right? And so that's what's really nice about that. So I will stop talking about that now, and I will go to the Q&A. So starting now, please type in any questions that you have with Q:, and then the question, so I can see it. And please keep whatever you ask to stuff that we did on today's stream or previous streams. If you want to ask an off-topic question, there is plenty of time for that, but we do it in the pre-stream. So we do it come about 15 minutes early from the scheduled starting time, and I answer whatever random questions you want at that time. So if you do have random questions at off-topic,
I hope he brings it back. I hope he brings the series back, and then I can sit in for these Q&As on day, you know, whatever 700 he's on, assuming he doesn't just scrap the whole thing entirely and start from scratch in some sense, because he's, you know, trying to decide which of those two things he wants to do. But the problem is that even doing this format day after day, like, there are so many questions. I feel like a dialogue is necessary. It's hard to, I think this is the thing that just keeps compelling me to keep going forward with this series and continuing to learn as much as I can until I get to a point where it's like I feel pretty comfortable exploring in any direction that I feel like exploring in. The periods of growth in my career, like where I could feel that what I was capable of and how the ways, you know, the extent to which my skill set was growing, the moments in time over the course of my career where that happened the most were in one of two different circumstances that I found myself in. And one was I was working closely with a mentor, and so there's one instructor in particular that I learned from when I was taking university classes that you know fits that archetype. There's also the mentor I had at my first proper full-time job. I learned a lot from him on the job. During those first, I want to say 1 or 2 years, trying to remember how long he was actually on the team. But while I was working with him every day, I learned so much just watching him work. And then the other circumstance in which I found myself growing the most was just tackling a very, very hard problem by myself and then like brute forcing my way through it without guidance or with very little guidance. Now you can like ask questions online. What I found myself arriving at a point with, once I realized I couldn't ask just strangers for help anymore, was when I got to a point where trying to explain the problem space to a stranger, like for instance on like a Stack Overflow question or something else like that, the questions became too nuanced. There was too much context to try and fit into the question to be able to ask it properly to get out a good answer. And that's why I think you see a lot of people who do have a lot of experience and answer questions. If the question isn't easily answered based on like the context provided, easily answered based on the context provided, if you have enough experience, the answer you're always going to have for that individual, unless they're willing to sit there and explain like the full details, they're going to tell you something like it depends, right? Because it truly does tend to depend on whatever the context it is that you're working with, you know? And I think that is why I'm compelled to do any of this the way that I'm doing it, because there's something about watching somebody actually do the thing that I find more educational than watching anybody talking about doing the thing. It is more rewarding that way. There is greater insight to be gained that way. And that's how things actually get done, is by doing the thing. And there's other examples of this being done, but I think in spite of the fact that the series is 10 years old, Casey's the one who's put in the most effort. It's also like the niche that he's working with, right? Like there's plenty of people in different niches. Like a good example, and I was just talking to Chelsea about this yesterday, or maybe the day before. She has spent a lot of time watching people who are good at crochet. She's learned from like other people who crochet and have all these accounts where they talk about, you know, these patterns that they're working on and the kind of stitch that they use to do the thing. And she's just watching people do the thing. You know, it's not, and I think, and then I was like, well, I imagine there's probably not a big group of people out there in the crochet community that are like bike shedding over crocheting techniques. And then she actually said I was wrong. There's actually people out there that are obsessing over details like that and doing themselves a disservice by getting lost in those weeds rather than just doing the thing, right? So it turns out actually, even with something like crocheting, that's a problem. But certainly for programming, that's like, if I look around at the state of things and I try and make sense of what all these different opinions are that people have about like what is the right language to use, or what is the right framework, or what is the right methodology. Like, it talks about doing these things as if there's just some universally applicable set of rules that you can use, almost like the equations that Casey went over during this day, you know, where it's like, here's the equations for motion, and here's, you know, the derivative of a position and the derivative of velocity. Like, you can just take that set of descriptors and then just use it everywhere in programming, as long as you like. So then it just becomes this problem where everybody's arguing over like what they think is the thing to use. And I think we just need more people doing the thing in general. And there are a lot of other people doing that that I've seen, but people don't seem to pay attention to that as much, partially because it's a bigger time investment. It's easier to just go and watch some like rage bait video where somebody, you know, either reaffirms your opinions or basically states the opposite of your opinion. So they're bringing in viewers, one of two viewers, basically people that are going to agree or disagree, and then that just becomes like that's just the whole thing. Is it's like one big argument over being right or wrong versus just actually going and doing the thing. So I don't know. I think this problem is like applicable almost everywhere you look. The example that I've been thinking of more and more is guitar. People will argue over, and like people with enough experience will come around to this position eventually where they say, you know, the kind of guitar that you want to use is going to depend on you, the individual, and also to an extent the music that you're trying to play with your guitar. But actually, you know, if it's like electric guitar, then you'll have people point out that the amp actually informs the sound, and therefore like the genre that you might be more inclined to play would how that would inform like your gear choice. But even so, what you'll see a lot of people start to say is just like, shut up and play the guitar, shut up and program, shut up and crochet, whatever it is, just do the thing, and quit getting in arguments about like what is the right way to do the thing, because you can't come up with a set of rules that universally apply in every circumstance for how to do the thing. So actually my son is waking up now, so I'm probably gonna have to wrap up the stream, but maybe we'll see if one of these first few questions are worth listening to Casey's answers on.
Let's see. So why use real physics instead of something more custom that can be hand-tuned? Well, we are using something custom that's hand-tuned, right? I mean, you just saw me hand-tuned it, right? We didn't try to go measure anything in particular, right? We didn't try to make this accurately simulate the motion of a human or anything. So the reason that we started with the physics equations is because, well, and you know what? This is actually a pretty important point. So let me really say this rather forcefully, actually. I try to keep game design opinions roughly out of the stream as much as possible, but I feel like this one kind of transcends game design and is more about just good programming and good game development. And that is, so many games that I see that are especially indie games, because they maybe are programmers who don't have as much experience with physics or whatever, they feel awful to control. And they had, you know, it was something custom that they just typed in and that they just, you know, tuned for whatever that definition is. But because they don't have perhaps the background or know the fundamentals of how physical objects work, they're never really able to get things feeling that visceral physical feel that you only get from starting with real equations of motion and then tuning them into the position that you actually want them, which is to not to say that they're going to be accurate, but having the full power of real physics behind you, knowing what those equations are and only violating them when you think you should, yields a game that just feels so much more natural to a person's brain, because all the stuff they expect to see happen to objects does happen to objects. Like if someone's trying to do a jump and it doesn't happen in a parabola style shape, it's a lot harder for them to intuitively understand how to make those jumps, right? And so a lot of times, like you want to start with that basic concept so that the player has a leg up on understanding it and using it. And then when you want to add air control and you want to add, you know, whatever, the double jump thrust or whatever, that's all great and you should do it. But you should start with the basics so that people's built-in understanding of how to predict the motion of objects, which has been hardwired into their brain from birth, isn't always having to do other stuff to sort of compensate for the fact that you weren't giving them the baseline that they probably should have for playing the game. And in our game already, we have one of those which drives me insane, and that's the wall stickiness thing, right? When I see that happen, it just feels awful. And so that's like the very next thing on my hit list, right? When I think about what I would want to do here, and again, it may not actually be the next thing on our hit list because I try to structure things in like educational order, not in when I absolutely think I would go do them because they drive me nuts order or whatever. That drives me nuts. And so what I want to see happen there is I want to see a little bounce, perhaps. I want to see a nice smooth glide along that. You know, I want to have a real nice feel for when I hit an edge, right? And so that already is not happening the way a physical objects don't stop when they hit a wall. They maintain momentum in the directions where the wall wasn't, right? They have that effect. And so I want to see that happen to the object because it feels so much better to have that actually happen. And so, yeah, so I highly, highly, highly recommend that no matter what your end goal is, start with the closest real physical equations that you can find to what you're trying to do, and then back off them as necessary to get the effect you want. Don't go the other way around, which is try to start just typing stuff in and hoping that you end up with something good, because I see that fail so often that I think there's a real risk there of jeopardizing the whole game because you don't get that feel of the primary motion correct. And
I feel like this inevitably leads to me spending 3 months rat-holing on the physics of fire and how fire spreads if I want to make realistic fireballs or, you know, realistic lightning bolts or whatever it is. Like, I'm thinking about all the implications of how this might inform a direction I choose to go in, and all of the time that I could easily waste just trying to come up with something novel in that direction. I don't know. Giving me some things to think about. I guess one thing, well, I'll see if that was a good question. Maybe the next question will be just as good, or at least the next answer.
And again, like I think I said in a previous stream, if you don't get that feel correct, nobody's going to play your game long enough to find out the other good things you may have put in it. Your game design may be great, but if it feels awful to move the character around, people are just going to like open it up and play it for a couple seconds, go, this feels terrible, and then shut it off, right? And like, you know, whoever's, you know, you try to submit it to a competition or something, and the judges play it for 5 seconds, and they go, oh, these people clearly just don't know what they're doing, we don't need to play anymore, right?
Like, it makes me think about, does Minecraft have good player motion? It's also blocky that it kind of disassociates your understanding of how things should behave, but like, I don't know. I guess in one respect, yeah, there isn't a whole lot of like physics really to even consider, like in the way that Minecraft handles it. Like, I'm pretty sure you swing a sword just as fast as you swing a pickaxe, right? So it's like, how much does this really matter? It depends on the type of game, as always.
And so it jeopardizes the whole game if you don't nail the compulsories, right? If you don't like basically just absolutely get those basic things.
Like, Minecraft isn't even trying to do those things right. It's not trying to do those things correctly, right? Like, Minecraft just gives you a whole different set of game stuff for you to deal with, which is like, you want to collect resources, you want to build them, and you can just build, a blocky, like, you could just build a bridge that just goes on and on and on with no support forever and ever off of a cliffside or off of a building or something, right? How much does it really matter? It depends on the game.
That everyone should get right. If you don't get those right, you risk ruining all the other things that you may have done really well. Like, you may have a lot of great ideas that happen at a higher level in the game, and if you can't get that core second-to-second feel right, you risk throwing all of that work away and having a game fail that could have been a success, right?
Conversely, like with a game, I'll just use Halo as an example, where it's like, when you are feeling like a tank that can take all of these plasma shots coming at you, and then you come in and you want to feel the weight of the punch as you cave in a grunt's head or something, that's when it matters a whole lot more. Whereas in Minecraft, I mean, if I'm thinking of like a mod, and this is not even a good way to apply this sort of thing, if I'm thinking of a Minecraft mod, it's not a good way to apply it, because like a mod can just do anything. A mod can be very good, but a mod doesn't need to be good for the game to have like that ecosystem to where you can have a bunch of different mods that try to implement like spell casting in Minecraft. I'm trying to think of all those different mod packs that I, spent an hour to install and then spent 20 minutes playing, where I'm like casting, it adds magic or whatever in some substantial way to Minecraft. And then you try and mess with it a little bit, and you're like, this is awesome, I'll have like Skyrim in Minecraft. And then you spend like 5 minutes doing that, and then you're like, wow, I should just play Skyrim instead.
And that could have been a lot of fun for a lot of people to play. So I can't stress it highly enough that like learning how to do really good physics-based programming, which doesn't mean simulation, it just means understanding the basic equation of motions and getting them right, is a really, really powerful tool, and I highly recommend that everyone learn it. And you can break the rules as much as you want to once you learn them, but just don't not learn them, because I think it will have a lot of really negative consequences for you when you're actually trying to make stuff feel good. Why not add an opposite directional deceleration based on V when collisions occur? Doing this slowly would allow the character to reach the final pixels close to the wall. Well, so we're going to be doing collision, and what happens around walls is very important, and so we'll be spending a lot of time on that a little further down. So hold that thought for when we actually start working with the wall stuff. Are you concerned that actual physics will detract from the purity and elegance of the world's greatest jump code? For those of you who haven't been with us the whole time, I was throwing something in to demo something very early in the stream, and I made this thing where I just threw a sine controller onto some. You don't even want to know what I did, but it was awful. And I think what I said, don't ever write this for jump code. Yes, I am afraid, I guess, that it might detract. Gosh, I hope it doesn't. Let's see here. What would you need to store if you wanted to reverse time a la Braid?
Ooh, that's a good... I hope he has a good answer for that. He should understand pretty well what the answer for that should be, or at least enough to give a compelling one, because that's something that I'm curious about too, because that mechanic all by itself is like what that entire game hinges on. And this is kind of like why I'm so interested in pursuing this domain, because something as simple, seemingly simple, as a really good rewind mechanic made this entire game. Now, could you make that game today and still have it be the success that it was in like 2008 or whenever it was released? I don't know, but something that simple can make, the whole thing. And then of course, like, there's stuff like marketing, right? That obviously has a huge impact on all of this. Like plenty of real cruddy games got a lot of good marketing. But I was thinking about this square thing that we implemented earlier, and then I realized I checked math.square, but for some reason I never checked like math.power or math.pow, and it turns out there's a math.pow proc. So, or maybe not. What happened? I saw it come up. Let's try this again. Math.pow. Function pow. So I can't just call pow. It has to be... No, shouldn't it just be able to infer? If I pass this in and I say math pow to... Yeah, okay. That's right. So now I can get rid of my square proc. Yeah. Looks good to me. What was that? That was in math. Yeah, that was just another one of many brain farts on stream. I don't know why I didn't check power, because like obviously you don't want to just be able to square. I mean, it makes sense that you want to be able to take the square root, but you don't want to just have a square procedure. You'd want to have, you know, a pow proc, so you can pass in whatever arbitrary power that you care to work with. And passing in 20 there really didn't do a whole lot. Maybe it feels a little bit quicker. A little snappier, yeah. Like we're not stuck going in one direction nearly as much. Like we can turn more on a dime. Yeah.
Well, that's kind of an open-ended question, so it's hard to say, but it does relate to physics very directly, and so I'll point this out. So
I'll let him answer this question and probably close out the stream. But was there a function called pow2? Will that just work? It looks like there is for specific types. So if I wanted to do that, and then, well, actually, yeah. Would that work? No. So you have to know what type ahead of time. And I just don't want to have to do that. I mean, I wouldn't yell at you for choosing to do it this way instead. Oh, shit. So that did something else. I don't know what that did, but that is not just squaring it. We can take a look. Pow2. Huh. If I look inside of Odin's packages, what do we see? Oliver was waking up, but then he decided to stay asleep, so I have a little bit more time than I thought. It doesn't say what POW2 is doing here, but I would have thought that that would have the same exact outcome as just POW, you know, the thing that you want to square and then, you know, 2. Right? Those my intuition is that those things would be equivalent, but it doesn't look like they are. Because we're doing something insane here. We're just shooting out of the map and back in, and it's crazy town. Why is that not showing up? Or did it just... Okay, yeah, it is showing up. I thought the game wasn't showing up. I was like, have I not been showing the game this whole stream? Yeah, so I don't know what that's about. But now I'm curious. not to get too sidetracked, but yeah, so I'm okay with this. Make sure we didn't call square anywhere else. I don't think we did. That is just unrelated there. So we're good there. Just took me way too long to find it.
So the rigid body dynamics simplification, remember I said we were doing rigid body dynamics, which is a simplification of physics that basically says, all right, I've got some collection of atoms, right, that makes up, this block that I want to simulate. And I'm going to simulate it by reducing it down to its center of mass, which is some position inside it, and its orientation, right? I'm just going to say that that's what I've got. And I'm going to simulate just that center of mass and that orientation, and I'm going to assume that all the atoms in the block just obey that and get moved along with it, right? That's the simplification. In that simplification, a lot of things just aren't real. They don't work the way that they normally do in terms of the microscopic level, because we're making a bunch of simplifications. And the eye can't see these differences, right? The reason rigid body dynamics is so useful is because it captures basically all of the interesting things that happen when non-deformable objects do stuff. Now there's deformable body dynamics, which allow things to squish and do other sorts of things, and that's a separate thing as well. It's another simplification, but ignoring that for a second. So the reason that we use it is because those equations of motion capture all of the things that our eye is used to picking up on, and we go, oh, okay, good, right? But one of the consequences of it is that it's non-reversible, right? So you cannot, for example, take the state of the world, flip all of the quantities, and run it backwards, and get back to where it was 15 minutes ago. And that's not because of our piecewise approximation, right? Our piecewise approximation is another thing that I'll get to in a second. But I'm actually talking about the actual non-participatory, if the user wasn't even controlling someone, the actual non-participatory rigid body dynamics are simply non-reversible. And the reason for that is friction. So basically what happens is when something slides along the...
Okay, this is not the answer that I thought we'd get when that person asked about, braid and rewinding. But I think that's just because he's taking the long road around to getting to the point, which is that I'm pretty sure that all that game did was just replay or rewind the game state, record every single state of the game as it's happening, and then just you have the option to play all of that back to the very beginning of the level. Versus like trying to calculate things going the opposite direction, because you can't do that unless you're recording at least the input, but then you have to know like DT for every single frame. Like either it all just comes back around to recording the input and the state as you were moving forward in time.
Ground, or when it hits air resistance, whatever, energy is lost from the system and things slow down. Now in the real world, that's not true. There's all sorts of stuff that happens in physics, and I don't pretend to know all of this stuff, but like, you don't really have stuff just slow down. It produces byproducts like heat that are, transferring atoms, like all of the quantum physics is happening. There's all this stuff that's happening. So to say that it was non-reversible is a very different statement, and I think it may actually be reversible. I don't even know. I don't know where physicists are on that kind of stuff. They come up with new theories, who knows? But what we do know is our simplification is very non-reversible, because basically what happens is the state of the world, let's say this was a die. Let's say this block was a die, a die that you play, craps with or whatever. You roll this die, it comes to rest on the table. That's the end of the entire information you have. So when that die, it bounces, it comes down here, it bounces, rolls, and lands here. If I wanted to get back that motion, if I wanted to reverse time to when the die was in the guy's hand before he rolled the die, well, I got no information to do that. His velocity right now is 0. I can't negate it and have him move back to where he was. And so that non-reversibility means that in order to do like braid style rewind, like you were asking, you actually have to store the state of the world at least at key junction points, like when things stop and when they're not in freeform ballistic phase motion, where you know that you can just play it forwards and backwards and it'll be the same. So anytime there is friction, you have that problem, because energy is being lost from the system and not accounted for anywhere else, right? Another way to do it would be to record the friction forwards and then play it back, whatever. The way Braid actually does it, I think, is just with compressed records per frame. Like, I think he actually just compresses like a rewind stream and plays that backwards, I believe. I don't remember how John ended up deciding to do that. But we would probably have to do similarly. Like, we'd probably have to do something where we stored records of guys' paths, because these things are non-reversible. You can't just play them backwards from state to state. You have to actually know what happened to the guy in the past, because the system is lossy.
Well, there you go. So I think that is a good place to stop the stream. I thought it was going to be a more coding heavy day. Had a few easy days, but it's fine because Oliver's properly waking up now. You can see on the monitor here. And so tomorrow I'll just keep on doing the thing, and we'll see what is tomorrow's topic. Reflecting vectors. So more vector stuff. It looks like there's going to be more whiteboarding again, which is fine. But I want to see how much, so I know whether to pre-watch. Yeah, it's going to be another day where like most of it is filled with whiteboarding stuff, so we'll see. Maybe I'll pre-watch that because I just want to dig into the more coding heavy stuff, which is there's plenty ahead, and especially once we get into the entity system stuff. That was the storage of entities and the parsing of them, getting them out of the memory block, the game's memory, and also doing like the SIMD stuff once that happens much later, like around day 100 something, whatever. All of that stuff, reinforcing all of that stuff is going to be what I'm looking forward to more than anything else, because reinforcing that will allow me, I think, to more easily go just do exploratory things with the code. Ballistic phase motion is way too intense a term when the example is tossing a die. Yeah, it feels that way, doesn't it? But that's what's so crazy about the universe, I guess. Like, there's always more aspects of what happens when you throw a dice. You can talk about the act of throwing a dice through so many different kinds of understanding. Like, people talk about, when you talk about like getting a good dice roll, like it's luck, right? But there's all this other, scientific mathy stuff happening when you throw a dice. It's actually kind of a fun example to play off of. And just the happenstance and chance, the expression that I've heard. I'd never thought of the term, God in this way, but when somebody said God is dice to me a long time ago, I was like, I'm not sure that's how I would have looked at dice before. But anyway, thanks for hanging in there with me and watching the stream. And we'll be back tomorrow to keep on working forward slowly towards building a game. And I'll see you then. Have a good rest of your day.